So we're doing 1.6 today. Let me go back to where we were last time. We talked about some transformations, specifically shifts up and down, left and right, and then we talked about even and odd functions last time. This time we are going to continue with compressions and stretches of parent functions. So if we have a function that looks like this, for example, f of x, and we were to multiply the f of x by a 2 or multiply the f of x by a 1/2, those are going to have different effects. Essentially what happens is when we multiply by 2, the graph is going to vertically stretch, meaning from like a center line, the graph is going to stretch up and down, right? So we're going to vertically stretch the graph. The window that the graph is in will probably not change because we're not changing anything about the horizontal orientation or the amount that the graph is stretched horizontally, but we are stretching it vertically. So this is going to become a taller graph when we do that, right? So when we multiply by 2 here, we're going to multiply all of the y values by 2. And if it's a positive value, it's going to become more positive, right? So a point like negative 2 comma 3 here, this first point, is going to become negative 2 comma 6, right? Which on the graph would end up being up here. So you see how that point, this original point, just became vertically further away from the 0 line, which is the x-axis. And if a value is negative, for example, this 1 comma negative 3 here, that's going to be vertically stretched away from the x-axis again. So 1 comma negative 3 becomes 1 comma negative 6 when we multiply the y values by 2. And that point here is going to be 1 comma negative 6. It's going to be way down here. The points in between we can also multiply. This was a 1, so it'll become a 2. This was a negative 1, so it'll become a negative 2. Negative 1 will become negative 2, and 1 will become 2. So we have negative 1 comma 2 here, 0 negative 2, and then 2 comma negative 2. 3 comma 2, and then we have our line that I want to ask a question about. So does it look like the graph got skinnier from the blue line to the green line? Does it look like it got skinnier?
Yeah.
Right. So that's an optical illusion, essentially. When we say skinnier, what do we usually mean skinnier, like pushed in from the sides, right? Like skinnier, left to right skinnier. This actually did not get skinnier because, as you can see, the graph is still spanning from negative 2 to positive 3, right? It's still going from negative 2 to positive 3. It's just vertically been stretched. So like I wouldn't call it skinnier because we're not actually squishing left and right at all. We're instead stretching it vertically, right? We'll see that it gets skinnier when we start messing with x values. This kind of transformation where we multiply the y value by a number, whether it's a fraction or a big number, that's just going to affect how the graph looks vertically. So when you pull this graph vertically, it's going to look a little bit skinnier because it's I don't know, it's a steeper angle, but it's not skinnier in the sense that it's occupying less space horizontally. Okay, it's occupying the same amount of same wideness horizontally. It's just been vertically stretched so that things are y values are higher and lower in general. Right. So what happens when we multiply by 1/2 instead? Well, 1/2 is a fraction that usually makes things smaller when you multiply them, right? If you take 10, you multiply by 1/2, it becomes 5. So y values, f of x values, when we multiply them 1/2 by 1/2, are going to get smaller. So We do that with the same numbers. We take these numbers here, we multiply them by 1/2, we put them here. So 3 multiplied by 1/2 is going to be 3/2. And then 1 multiplied by 1/2 is 1/2. Negative 1/2. Negative 3/2. Negative 1/2. And 1/2. It would have been nice if they chose even numbers for us to do this with, but they did not. So let's try to graph these on the same graph. So negative 2 comma 3/2. 3/2 is 1/2, so we go negative 2 comma 1/2, which would be here. Negative 1 comma 1/2, which is here. 0 comma negative 1/2. 1 comma negative 3/2. 2 comma negative 1/2. And 3 comma 1/2. So that's going to be our red 1/2 f of x graph. Again, left to right, it's occupying the same window as the original graph. All we've done here is kind of squished down by pushing the y values closer to the x-axis, right? And now squishing down is what we call a compression. Right, so I guess I can label them here. This 2 f of x we would write is a vertical stretch by a factor of 2 because all of the y values were multiplied by 2. And then this 1/2 f of x, we'll write it down here, is a vertical compression by a factor of 1/2. Because multiplying by 2 makes things larger, it's going to be a stretch. And because multiplying by 1/2 makes numbers smaller, it's going to be a compression. We're going to get a actual theorem here for when it's a vertical stretch and versus when it's a compression. Important things here are this looks exactly like the functions that we just worked with, right? So vertical stretch or compression must have to do with just this a value that's being multiplied by the f of x. So if a is a constant, then it's either a vertical stretch or compression. In general, if we multiply the y, it's going to be a vertical stretch or compression. And the rule is that if a is greater than 1, like the 2 in the previous example, that's a vertical stretch by a factor of a. And if a is between 0 and 1, then it is a vertical compression by a factor of a. So if you multiply a number by a number between 0 and 1, it's going to make it smaller, so vertically compress. If you multiply by a number greater than 1, it's going to be vertically stretched. What happens if a is 1? Because that's not really considered in these two examples. What do we think happens if a was equal to 1? What if a was 1?
Would it be that nothing would happen to the graph?
Right, because if a was 1, then g of x, the new function, would just be equal to 1 times the original function, which means the new function is just equal to the old function, right? There's no, the 1 multiplied by 1 doesn't do anything to the y values, so there's no stretch or compression. It's just identical to the original function. So if a was negative or less than 0, then there's a vertical reflection, and then depending on whether or not it's between 0 and -1, or if it's less than -1, like -2, -3, then we would have a vertical stretch or compression along with it. So if, for example, if it was g of x is equal to -4 f of x, the negative part is the part that makes it reflect vertically, and then the 4 would make it vertically stretch, right? Because the 4 is greater than 1, and the negative is making it reflect over the x-axis. Right, so that's vertical stretches and compressions. Let's talk about horizontal, and then we'll see if there are any questions. We can do the same thing, well, something similar, by multiplying the x values by numbers, right? So here, instead of multiplying the y values, we're multiplying the x values. And you can tell that that's happening because the number that we're multiplying by is inside the parenthesis with the x. You'll see this represented in functions when you look at, is there an example? When you look at something like this, a function like this, and on the last page of the section, you'll see that this 1/2 is being multiplied by the x rather than the function, right? If the 1/2 was out here, then it would be the whole function that we're multiplying by. But here, we have the 1/2 next to the x, which means it's affecting the x values. So going back to our example here, we're not going to do the first two boxes here, because we don't have values for those in the original function. But when we want to do g of -1, we're going to instead do f of -2, because we're multiplying the x value by a 2. And f of -2 from the original graph is this -2 comma 3. So we get a 3 here. And then g of 0 is going to be f of 2 times 0, which is 0 still. And that's going to be -1 from the original table. G of 1, which will be f of 2, because we multiplied the x value by a 2. And f of 2 from the original graph is going to be -1. And we won't be able to do g of 2 because that'll be f of 4, but we don't have a value for f of 4. So we won't be doing, we don't have data for the last two parts either. So we've graphed these 3 points here. -1 comma 3, 0 comma -1, and 1 comma, wait, okay, 1 comma -1. Now the issue here is we're missing some points, right? This is supposed to retain its shape. We're just stretching or compressing this graph. So these 2 points that were originally, where is it? These 2 points at -1 that were originally here and here are now here and here. So those are the analogous points, right? Those 2 points got compressed to there, which means this point down here will remain down there. This is going to go all the way down here and then come back up to we're actually going to come back up to here because that's the range of the original graph gets retained. All that happens is the graph gets horizontally compressed, so the highest point and the lowest point on the graph should be preserved because there is no vertical stretch or compression happening. So if our highest point was 3 and our lowest point was -3, then our highest point should still be 3 and our lowest point should be -3. This endpoint is at a level of +1 on the y-axis, which is the same as the original graph. So vertically, there is no stretching or compressing happening here. This is all a horizontal compression. Originally, our window went from -2 to +3. Now that has been shrunk down to go from -1 to +1.5, right? So horizontally, our window got cut in half, or the -2 became -1 on the leftmost point, and +3 became +1.5 on the rightmost point. Some of these points are not represented in the table here, but if you were to take points from here, like this point here, 3 comma 1, that got horizontally compressed to 1/2 comma 1. So this, let's make a note, is a horizontal compression. By it's a horizontal compression by 1/2. I know we're multiplying the x values by 2, but horizontal stretches and compressions kind of act in an opposite way, where if you multiply by 2, it's a compression by 1/2. And we'll see that when we multiply by 1/2, it's going to flip and do the opposite of what we expect it to do. It's going to be a horizontal stretch by 2. So let's do that one real quick. H of -4 will be f of -2 because we're multiplying that by 1/2, which on the original table is a 3. And h of -2 will be f of -1 because we're multiplying by 1/2, and then that from the original table is 1. This one's not going to show up on the original graph because there is no f of -1/2. H of 0 we should be able to do. Multiplying the 0 by 1/2, we get f of 0. F of 0 was -1. This again will not show up on the original table. H of 2 will become f of 1 when multiplied by 1/2, and that from the table is -3. And then h of 6 will be f of 3, which from the table is 1. So when we plot these points, we're plotting these x's to these y values that we got, so -4, comma 3. Is here. -2, comma 1. 0, comma -1. 2, comma -3. And 6, comma 1. There does seem to be a bit of weirdness happening here. This has kind of a symmetry to it, right? There's the slope going down here is the same as the slope going up here, or it's like reflected over. Why was it preserved on that one, but not preserved on this one? Oh, I'm sorry. It's 6 comma 1. We graphed that wrong. That last point was graphed wrong. 6 comma 1 is up here. There we go. Okay, now it's preserved, which is what we expect to see. But what happened here? We see that the original graph goes from negative 2 comma 3 down and then up to 3 comma 1. But here this point got stretched out to here. And then this last point got stretched out to here. So we see a horizontal push. Actually, we see a horizontal push from here, from the y-axis, stretching this out to be horizontally wider, right? So we have a horizontal stretch here. So multiplying the x values by 1/2 is a horizontal stretch by a factor of 2. So multiplying the x values by a 1/2 actually stretched the horizontal graph by, or the graph horizontally by a factor of 2. So whenever we multiply the x value by a number, that's going to be kind of opposite to intuition, where if you multiply by a number that is between 0 and 1, then you're going to have a horizontal stretch by a factor of 1 over b. And if your b that you're multiplying the x values by is greater than 1, then you're going to have a horizontal compression by a factor of 1 over b. So the compression and stretch happens by a factor of 1 over b. And then if you have a negative b, just like the vertical reflection, if we have a negative b, we're going to have a horizontal reflection over the y-axis, and then we're still going to have a horizontal stretch or compression based on which two of these categories, or which of these two categories the b falls into. Okay, let me pause there for any questions on vertical or horizontal stretches and compressions. Okay, maybe you'll have questions when you actually are working on these problems. So, combining transformations. I'm going to let you work on these. Let me talk about this here because this kind of puts everything together. We have vertical changes and horizontal changes all in one standard form. Let's talk about this expression here in standard form and kind of highlight things here. Things that are going to affect, so the original things are we have y and f of some function, right? So those are standard things. This f is just a standard function notation. Everything else in here, well, x and y are also just variables. The a, the b, the h, and the k are going to be transformations, right? So the vertical transformations are the a and the k. So those are going to determine what kind of vertical transformations your graph is going through. A being multiplied by your function f of x is going to be a vertical stretch or compression. And if a is negative, that's what this first one is saying. We reflect vertically across the x-axis if a is negative, and then we vertically stretch or compress by a factor of absolute value of a, just a positive version of a. So the a in front of the function is going to be either a vertical reflection if it's negative, or or a vertical stretch or compression. And then finally the k is the vertical shift. Remember, if k is positive, your graph shifts up. If k is negative, then your graph shifts down. So that's this last part here. You shift up or down by k units, right? So focusing on the a and the k, we can figure out what's happening to the graph vertically. It's either getting reflected, stretched, compressed, and then shifted up or down. And then the b and the h in this form are going to be horizontal changes to the graph. If b is negative, then we will horizontally reflect across the y-axis first. And then, depending on whether b is greater than 1 or less than 1, we're going to stretch or compress by a factor of 1 over b, because the horizontal is kind of opposite. We do a reciprocal of b when we're doing the stretches and compressions. And then finally, the h is going to be a shift left or right. So putting all of those together, you can look at an expression like this and figure out all of the little things that are happening. For example, this minus 3 is going to shift my original graph down 3, right? Because I know that's the k from my standard function. That's my k, and that's a minus 3, so we're going to shift down by 3 units. And this negative in front of the f is my a. That's a negative 1, which means I'm going to reflect vertically across the x-axis. I'm going to do them in this order. So this does give you an order of things, order in which to do things. That's why it says lastly we shift up or down. There's an order to this. We do reflections first, and then stretches and compressions, and then shifts. The only thing I'm going to say about this last example is that the way this is written in standard form is pretty important. It needs to be in this form before you can work with these vertical and horizontal changes. This is not exactly in this form yet. What is the issue with this, the way this is written? How is it different than this standard form? There's a slight difference in the way that they're written, form-wise. Can anyone see that?
Is it because 1/2 is applying to x and not the h? I don't know.
Yeah, that's a great point. It's exactly what this part looks different. The part inside the f parenthesis. Here we need the b to be multiplying a parenthesis. If there's an h, that b needs to be kind of separated out from that h. So here, this 1/2 is only multiplied by x. This is not influencing this 1/2. So we actually need to rewrite this as a, I'll just rewrite the whole thing, a negative f of 1/2, and then I need something in here, and then the minus 3 outside. So we need to convert it to look exactly like this standard form that we have up here. So if I wanted to do that, that's essentially factoring a 1/2 out of the 1/2 x and the 1. When I factor a 1/2 out here, this essentially means that if I distribute this 1/2 back in here, into this parenthesis, I should get back to the 1/2 x plus 1. So what number is my h going to be here? Or what number do I put here so that when I distribute this 1/2 back in, I get back to this original function that we started with?
2.
2, good. So when you factor a 1/2 out of this parenthesis, not out of the f of x because we're not taking it out of there, but we're factoring out of the 1/2 x and the 1. We factor that out, we have an x plus 2 in the parenthesis, so we can identify some factors here. We have an a, we have a b, we have an h, and we have a k. All right, so we should identify those 4 things before we start doing the vertical stretches or compressions or horizontal stretches and compressions and stuff. So what is my a here? A being the number in front of the f. What is my a?
-1.
-1, perfect. What is my b?
(1/2).
Perfect, 1/2. What is my h?
2.
No. What is the h?
-2?
It is -2. Why is it -2?
I mean, because we moved to the left, right? It's just kind of how the formula is.
Yeah, we are going to move to the left. So it is backwards because this is plus 2. We're going to move to the left. But the reason why that's happening is because this original standard form is x minus h, right? So if this is going to be x minus something, then that something must be a negative 2 because we're seeing x plus 2, right? So in disguise, this x plus 2 here must be like an x minus a negative 2. Right? If we needed to write that as x minus something, we would have to write it as x minus a negative 2 in this parenthesis here. So that's the h here is the negative 2. Finally, what's the k?
-3.
Yes, negative 3. That one is not going to change because the original formula has a plus k. So this plus number here is a negative 3 that we're adding to the function at the end. So based on those 4 things, you should be able to figure out what vertical and horizontal changes are happening and then apply them to this graph. Okay, make sure you're doing them in this order when you're doing it. This last part says horizontal and vertical transformations are independent. It doesn't matter whether you do the horizontal or vertical first, because when you're doing horizontal stretches or shifts or whatever, that shouldn't affect any kind of vertical aspect of the graph, right? When you're doing anything horizontal to the graph, it should remain in this window here. You should either, if you have stretches or reflections or shifts, it should shift right and left between in this window here. It should stretch horizontally in this window here. It should reflect across the y-axis if it's reflecting, but it should never leave this window here. And then when you're doing vertical changes to the graph, wherever the graph is, it should not leave this window here. It'll either stretch vertically, or it'll shift up, it'll shift down, or it'll reflect across the x-axis. It'll never leave that window. Now, if you shift horizontally to a new window, then obviously it'll remain in that window when you're doing your vertical stretches and shifts, right? But vertical and horizontal should not affect each other.